This video is about section 1.9 in Anton, about the composition of matrix transformations. And the question it's trying to answer is, why is matrix multiplication so strange? You take, define the ij entry, you take row I in the first matrix, dot multiply with it by column j, and then add the result. Why is it so complicated? Why not just take each term in one matrix, multiply it with somehow corresponding term in the other matrix, and that's the product? But no. Anyway, the short answer is that the matrix multiplication of two matrices B times A, B is a matrix of dimensions L rows and M columns, A is a matrix by having M rows and N columns. Because these numbers here, M, agree, we're allowed to multiply them, and the result will be a L by N matrix. But anyway, this strange matrix multiplication is the matrix associated to the composite of the transformation T sub A followed by T sub B. So let's recall what these transformations are, as well as you might be wondering, well, okay, why do these transformations even matter? I won't get into that in this video, but it turns out that things like rotations and translations that often appear in computer graphics, those are given by these matrix transformations, and so composing them amounts to multiplying such matrices, and that's how it comes up in practice. Okay, so again here, A is a M by N matrix, and that means that we have this linear transformation T sub A defined by left multiplication by A, and it takes a vector that has n entries. So V is an n by 1 column vector, and when you multiply on the left by A, you get an m by 1 column vector, so an element of Rm, an m tuple of numbers. And geometrically, V is the input. You apply this function or linear operator or map to V, and you get some other vector in a different space called A times C. And then we can do the same thing if we're given another matrix B that's of the appropriate size. Remember, an M by N matrix maps vectors in Rn, the number of columns of A, to vectors in Rm, where M is the number of rows. Okay, so if we want a map from Rm to a third space, Rl, we need an L by M matrix. So that's why B, I'm assuming, is an L by M matrix. And so then the transformation corresponding to left multiplication over B sends something in here, Rm, to something in RL. And then the definition of the composite, TA composed with TB, it's somehow read from left to right because TA is the function or transformation you do first, then you throw whatever T sub A gives as output into the input for T sub B, and that spits out something over here. And the composite is denoted by T sub A composed with T sub B. And okay, so the theorem is that this composite map from Rn to RL is equal to the transformation given by the matrix multiplication of these two matrices, B and A. And right now, it's maybe not so important, the proof, but I want to go through it just to emphasize or to give some idea of why do we care about the strange matrix multiplication. And the reason, which is a little hard to appreciate at this point, is that matrix multiplication corresponds to taking the composite of the transformations associated to the two matrices. So let's go through the proof, which again is not so essential, it's going to take a little bit of concentration and doesn't involve a whole lot of numbers, instead involves a whole lot of letters, so if your eyes glaze over, that's perfectly fine. All right, so the first step is to show that this composite, T sub A followed by T sub B, is a linear transformation. Now, a linear transformation has two properties. Here's the first one, that if you add two vectors and apply the linear transformation, or the transformation I should say that we're trying to show is linear, then the result should be the same as what's down here, applying the transformation to each vector and separately, and then adding the result. All right, so let's see why that's true. Well, by definition, the composite is you take the first transformation, T sub A, that's actually written secondly, and then apply it to your input vectors. In this case, our input vector is u plus v. Okay, and then apply T sub B to that output. So we start with u plus v here, apply T sub A, and then, so that's this output here, and then we throw that output into T sub B, so we finally land over here. Now, T sub A applied to u plus v, well, we've seen in a previous video that T sub A is a linear transformation, so T sub A applied to u plus v is T sub A applied to u plus T sub A applied to v. Similarly, T sub b is a linear transformation, and so T sub b applied to this, the sum of these two vectors. These two vectors live here in Rm, and so because it's a linear transformation, we can apply T sub b to each of those vectors individually and add. Okay, so, and then T sub b applied to T sub A of u, by definition, that's what T sub B composed with T sub A is. And similarly here. So we've indeed shown that this composite satisfies the first property of a linear transformation, namely that it's additive, essentially. That when you apply the transformation to u plus v, that's the same thing as applying the transformation to u, applying the transformation to v, and adding the results. The second property of a linear transformation is that you can move scalars through it. So I won't go through the details of this line here, but basically we start with the scalar k, and using the fact that T sub A and T sub B are linear transformations, we can essentially move the k past the T sub A and the k past the T sub B, and there we have, actually I did go through that, it was quite easy. Okay, so all right, so we have a linear, that this composite is a linear transformation. And so what's the point of that? Well, we've seen in a previous video that there's a theorem that says any linear transformation comes from a matrix, is the transformation associated to a matrix. And so using that theorem, we see that there is some matrix M, it's got to be of this size, such that T sub M is equal to this composite transformation. And what we're going to show on the next page is that this M has to equal whatever the strange matrix multiplication B times A is. All right, to show that M is equal to B times A, what we're going to show is that the ith column of M equals the ith column of this product B times A. Now, the ith column of M is M times EI, the ith standard basis vector, which is the same thing as T sub M applied to EI. That's this fact we saw in a previous video that's used repeatedly, that to pick out the ith column of a matrix, you multiply the matrix by the ith standard basis vector. Okay, so Tm of EI is equal to TB, TA applied first, then followed by TB, and then you apply that to EI. By definition, you start with EI, apply T sub A, apply T sub B, and all right, now to apply T sub A to EI, that picks out the ith column of A. And then, okay, then T sub B is just left multiplication by B. And if we think of B as a matrix, L by M matrix, and write out the rows of B like so, and then imagine, what does matrix multiplication do when you multiply this matrix by this matrix? Well, first of all, that because M and M agree, we're allowed to multiply these matrices, and the answer will be an L by 1 matrix. And then, so here's what I've drawn, an L by 1 matrix. And in row 1, column 1, we'll take row 1 of the first matrix times column 1, there's only one column, of the second matrix, and dot them. And so that's B1 dot product with AI. Similarly, in row 2, column 1, the 2, 1 position, we take row 2 of B dot with column 1 of our matrix here, and that column is AI, the ith column of A, and so we get this, and so on. Okay, so that we figured out that this thing, the strange thing, is the ith column of M. Next, what we have to do is figure out what the ith column of B times A looks like. And this involves thinking back to what that strange definition of matrix multiplication. And to get the ith column of B times A, what you do is multiply the various rows of B, always, or dot them by the ith column of A. So that may take a little bit of thinking or drawing in an example, but if you think about it, then you get that the ith column of B times A is you start with the various rows of B, and stick though with the taking dot product with the ith column of A, and that's exactly what I've written here. And so what we see is that the ith column of M, which is way up here, is equal to the ith column of BA, since this matrix and this matrix, if you stare carefully at the indices, they're all equal to each other. And so since the ith columns of M and BA agree, for every I that's involved from 1 to n, that means that these two matrices are equal. And that's what we want to show. Okay, so this proof was a little bit technical, but it's not something you have to master, but I did want to go through it just because psychologically maybe it's important to know that there's some reasoning for why matrix multiplication, first of all, is so useful or comes up so often, and also why it's so strange.